Okay, now we'll start chapter number 31. This chapter will include Faraday's law, Lenz's law, motional EMF, and generators. So we'll start with Faraday's law. Faraday worked on this circuit in his lab, the one which is shown over here, and he wanted to induce current in a loop which does not have any source of potential with it. So he had this loop 1 with which he attached a potential source and a switch and a solenoid. And when the current flows through this solenoid, there is a uniform magnetic field within the solenoid. And then he had this loop 2 which has no source of potential, and he wrapped this tube around this solenoid, and he by uh, letting the current flow through this circuit, he wanted to induce current in this loop 2, but he did not succeed initially. One day while he was working in his lab, he noticed that when he closed the switch, uh, and a current is produced in loop 2, and the moment he opened the switch again, he saw a current induced in loop 2. So he concluded that changing magnetic field is causing current. So therefore a current and an electric field can be produced by changing magnetic field, and that is called electromagnetic induction. Now let us suppose that we have a closed loop over here, and there is a bar magnet, and if we approach this magnet towards this loop, we'll see that the current is induced in the loop, and the magnetic field is in the direction upward. So if the bar magnet is approaching the loop, the field will be in the upper direction, and the current will be anti-clockwise. And when the bar magnet is drawn away from the loop, the direction of the field will be downward, and the current will be in the clockwise direction. The current will always go in such a direction that it opposes the change of magnetic field, and this opposition that the current shows is known as Lenz's law. So the current wants to oppose the change in the magnetic field, and this is known as Lenz's law. Lenz's law helps in determining in which direction these induced currents will run. It will not tell us about how much current is flowing, but gives us info about the direction of the current. So mathematically we can write induced EMF equals to induced current into R. This is Ohm's law. And Faraday conducted different experiments, and he measured that when the magnetic field is varying with time, then we have induced EMF in this second loop. So induced EMF in the second loop is directly proportional to the rate of change of magnetic field in the first loop, and induced EMF in the second loop is directly proportional to the area. So now if we combine these two parameters together, we'll see that we have d by dt into b dot a, and from our previous knowledge we know that b dot a is a magnetic flux, and we can replace this as induced EMF is proportional to d phi b over dt, and we place a negative sign over here, and this negative sign is for Lenz's law, which shows that motional EMF always oppose the rate of change of magnetic flux. Now suppose we have this surface, this closed loop over here, and the area shown over here is pointing in the upper direction, and the magnetic field is in this direction. The magnetic flux through this area is defined mathematically as d phi b is equals to integral open surface b dot dA. If phi b is varying, Then we have induced EMF in the conducting wire. Let us take a conducting wire having surface and magnetic field is coming out of the blackboard, in this case out of the laptop screen, and we are considering that the magnetic field is increasing with time. So we can write this induced EMF equals to minus d phi b over dt, and this is also equals to minus d by dt integral b dot dA. Now, as the current is induced in this closed loop, because of the presence of the current, we have electric field, and the direction of the electric field is in the direction of this length element, and all current, electric field, and dl, they are in the same direction. So, for this closed loop, we have this closed integral E dot dl, and all of these they tell us about Faraday's law. So if the current is flowing in the wire, there will be an electric field which is shown in the figure. If there is no electric field, then there will be no current. So this is all about Faraday's law, and these equations tell us that for induced EMF, we can have induced EMF if we have rate of change of magnetic flux, and this can be written like this, and this induced EMF is also equals to closed loop E dot dl. Now we can write this induced EMF as minus d by dt BA cos of theta, because we have B dot A, which is a scalar product, and if I expand this scalar product between B and A, I get BA cos of theta. So EMF can be induced if we change magnetic field with time, if area is changing with time, and if the direction or the angle is angle between the magnetic field and area is changing with time. So all these factors contribute to induced EMF. Now, application of Faraday's law are in generators, motors, transformers, electric bells, electric guitars, and ground fault circuit interrupters. So this is all about Faraday's law.